We study C12 trigonometric addition formulas and Euler's formula. We learned how to rotate vectors on a plane in the two-dimensional plane, and the rotation matrix rotates Cartesian components into prime, and we insert the rotation matrix R theta, and that is a cosine, sine, minus sine. You have to remember. Prove that the multiplication is commutative, and actually on the plane we keep the same axis of rotation, that is z-axis. In that case, I can rotate by theta 1 and then theta 2, and I can also rotate by theta 2 first and then theta 1. As a result, the resultant rotation is just the sum of these two, and this sum is the same as theta 2 plus theta 1. So without any explicit computation, evidently it is manifest that the product of rotation matrices must be the same as a single rotation matrix if we keep the axis of rotation the same. However, it is not true if we change the axis of rotation. So this is a special case. We keep rotating with the unit basis vector along the z-axis. By making use of the rotation matrix, prove this sinusoidal addition formula. Okay, let's see. The rotation matrix is RA multiply RB. So we just copied this. So this, wait a second, what's that? Okay, this is the first row, first column. Multiply this cos minus sine. Okay, and then second row, first column, sine cosine sine cosine sine. That's fine. And the second column, first row, second column is this cosine sine minus and sine cosine minus. And finally, this one can be obtained by multiplying this second row and second column. The result is minus sine plus cosine. Okay, as a result, we find these and these, they are the same. And these and they are the same except that we have negative sign. We remember single rotation by angle alpha plus beta is according to the definition of rotation matrix. I substitute alpha plus beta for this theta. Okay, as a result, because they must be the same, I compare one by one. This is this. This is this. Cosine minus sine. Okay, this is a sine alpha plus beta. Okay, sine cosine sine. We have proved this addition formula for the cosine and sine functions in a trivial way. Rotation matrix can be multiplied by n times. In that case, if I multiply 2, the result is 2 theta. If I multiply one more, then 2 theta, and some of them, 3 theta, and so on. So if I keep multiplying r theta by n times, the result is, it is apparent that it's a single rotation matrix by n times theta. So for n equals 0, it is nothing but cosine 0, sine 0. And cosine 0 is 1, sine 0 is 0. So it is an identity matrix. If we do not rotate, the rotation matrix is nothing but the identity matrix. And we can prove this relation by mathematical induction we are very familiar with. 0, substitute, that's fine. Inverse is nothing but the r minus theta. Why? We rotate by angle of theta, and if we rotate by angle of minus theta, then the resultant angle is theta minus theta equals 0. If I don't rotate, that is identity. Aha, therefore, r theta multiplied by r minus theta is r0, that is identity matrix. R minus theta multiplied by r theta is r0, that is identity matrix. Therefore, inverse transformation to inverse rotation is nothing but the replacement of angle theta by minus theta. Okay, so inverse is r minus theta. Trivial. Third, consider rotation matrix of the xy plane by an angle theta. Okay, because r theta to the nth power is r n theta, why don't we replace this theta with theta over n? Then it's r theta over n, and n equals r n times theta over n. That is r theta, right? Therefore, a arbitrary rotation matrix of angle theta about a single axis, that is a E3 axis, that is identical to the multiplication of n times of this rotation matrix. By the way, we find a matrix A such that I r to the r theta is expanded in this form. Let's see. First, we take the limit as n goes to infinity. Then we can see this one is always the same whether we attach this limit or not. It is exact for any integer, including positive integer, including 0. Okay, we remember exponential I theta, real part is called the cosine, that has the expansion form. Imaginary part of e to the I theta, that is sine theta. Actually, this is Euler's formula. E to the I theta is cosine theta plus I sine theta. Okay, that can be obtained by expanding this e to the I theta as a power series of k runs from 0 to infinity, k factorial, I to the k factorial, theta to the k, and this sum can be divided into two pieces, even powers and odd powers. In that case, we arrive at the final result that real part is cosine and odd part is sine. Okay, hence in the limit n goes to infinity, we have in here cosine theta over n, sine minus sine theta over n, sine theta over n, cosine theta over n matrix. As n goes to infinity, it becomes a very, very small number. If it is a very small number, the expansion of this power series is 1 minus 2 factorial theta squared, and so on, plus 4 factorial theta to the fourth, and this is the theta minus 3 factorial x theta cube, and so on. But in the limit as n goes to infinity, what we find is 1 plus very tiny with theta over n squared. And here, the leading piece is theta over n. As a result, we can expand this as a power series of theta over n. Leading contribution is a diagonal component, that is identity matrix 1. And subleading contribution is proportional to theta over n, that appears in here and here with -1 and +1. Okay, and then the next order is theta squared over n squared. So we put this one to be keep everything higher of order theta over n squared and higher. So this was the identity, and then we write this, copy this one in here, this identity matrix, and this is theta over n, and this A is nothing but this matrix, and then additional matrix. And then we take the power, n goes to infinity. We are very familiar with the algebraic expression 1 plus 1 over n, and limit n goes to infinity equals e, and if there is a number, it was this, and this was a sum of k goes to 0 to infinity k factorial x to the k. Haha! What we have found is nothing but this is just like a number, and this higher order piece in the expression or higher, we knew these vanishes completely. So this one is nothing. As a result, this one is e to the theta a. And what is e to the theta a? Sum k goes to 0 to infinity k factorial theta a matrix k. This infinite sum, this series, represents the rotation matrix. Okay, this is what we have found, and as we have done with the usual exponential function, matrix exponential also reproduce this power series expansion. By the way, this matrix has a special condition. This one is a 0 minus 1 multiplication will give -1 in here, -1. And this one gives a 0. This one gives a 0. And this one gives -1. So this is nothing but the identity. It is very similar to the pure imaginary number I squared is -1. As a result, if I have I to the 2k, it is a -1k. I to the 2k plus 1, it is a minus k and I. So in the summation, including e to the I theta, we have obtained cosine theta plus I sine theta in this due to this relationship, and we have identical relation. Therefore, our final result, this one, this diagonal part, that is a squared is identity, a squared is identity multiplied -1, so just like I squared is -1. So using these two relations, we have odd powers and even powers, and even powers are proportional to the identity matrix, and odd powers are proportional to the matrix A, that is this -1, 1. As a result, we define this one f theta and g theta Okay, this sum. And then finally we can make use of previous result. Original result, we began with this one. It was cosine minus sine, sine, cosine. However, what we have found in the sum of this matrix series, what we have found is identity multiplied by this series and this series. What are the coefficients? This is f and g. And what is f? F is a cosine and g is a sine. Therefore, at the beginning, we thought we are making use of this. However, without that assumption, what we have found from the rotation matrix, I can even verify that these are cosine and sine. So it is a remarkable result by Euler's formula. Next one is rotation is in general not commutative. So if I use a different axis of rotation, we will find the product is 1, 2, and 2, 1. The final results, they are some elements are the same, but these elements are different. These are different. Okay, so in general, matrix product is not commutative. The commutative relation holds only for the case in which the axis of rotation doesn't change at all. Finally, we make use of these three 2x2 matrices. This is called Pauli matrices. Who discovered the spin of an electron? And due to Pauli, we were able to find the quantum mechanical view of a hydrogen atom for the first time. He is the person who solved the hydrogen atom energy level problem for the first time. So that is the triumph of quantum mechanics. So compute the square, it is very, very similar, but in this case, a square, this I have shown on all the details of calculation. Their squares are all, even though they are different, the squares are identity matrices. Because of this special relationship, I can find the odd even powers is always identity. Odd powers is just their single power. Oh, because of that, we can make use of this kind of series expansion of exponential I, some real parameter, and this sigma, where z is 1, 2, 3, so separately. Again, we make use of the summation. We are familiar with this. They are cosine and they are sine. Okay? Finally, this one can be this kind of one can also be applied to the Lorentz boost. This is the boost matrix. Is the for the space-time transformation rule for the special theory of relativity. And in this case, we have a transformation rule very similar to cosine, sine, minus sine, cosine. That is rotation matrix in the Euclidean space. However, we have a very special rotation for this transformation of time and space. So it is not Euclidean anymore. It is Minkowski space. Minkowski space in which we are living in. So time and space construct. We have chosen only a single direction, but actually we have x, y, and z. So we have a three-dimensional space and one-dimensional time. So this transformation of space-time coordinate, according to Einstein's special theory of relativity, is determined by the hyperbolic, cosine, and sine. And we just make use of these identities. Why don't we apply the same rule for the boost n boost with 1/nth of angle? Then this is identical to the rotation, series of rotation. So series of boost. If I take the limit as n goes to infinity, very similar to the sine and cosine function, we have this kind of form. Okay, so we can make use. We will consider this one more in detail later. That's it for today.